Okay, so we're going to go through a sum of an infinite series. Now in this one they've given us just terms. Okay, and we know we have our term 1, right? So this would be our T1, T2, T3. Now this is a sum of. The first thing we got to figure out if this is a geometric series or an arithmetic series. So to figure out if arithmetic is obvious that it's in decreasing in values, right? So if we quickly subtract, this one, if we decrease, went down by 0.5, where this one went down by 0.45, it looks like. So already we don't have a constant, right? So we know it's arithmetic is not what we're looking for, right? Because it's not going down by the same amount. So let's check out a geometric sequence, in which case we divide our values to see if they're going down. Because usually geometric sequences are considered like an exponential equation. So if one way you could think of it is like starting here and we go 5, 4.5, 4.05, and we just take the bottom term and continue to divide up. Okay, and that should tell us what our decay rate is because this is going down. Okay, there you go. So let's start at the very last one actually. 4.05 divided by 4.5. Okay, 0.9. So this is saying that you multiplied by 0.9. Let's try the next two values. 4.5 divided by 5, 0.9. Okay, so though they haven't given us a lot of information, it looks like the sequence is that it's going down by 0.9 every time. Okay, so that means we do have a geometric series. And the sum of a geometric series is written as S at n is equal to A, which is our first term, multiplied by R, which is our growth or decay rate, to the power of n being the last term, subtract 1, all divided by the growth or decay rate again, subtract 1, R minus 1. Now in this case, because they've given us no ending, essentially what we're saying is this is going to be a series that goes on forever. So we're looking for the sum of our values, and because our first term starting at 1, we'll use this value, or in this case we used an n, so we'll say n as it's equal to 1, so as it starts. We can build this exponential equation. Usually exponents are written as, and I think they have geometric sequence written very similar, A, and they usually use a value of B, but we'll call it R because it's R in our equation, which is our growth rate, to the power of n. This is our formula here. So we figured out, we know our A value, which is our starting point, is 5, and our R value is 0.9. So we can build our series here, or at least our question. Because it's infinite, we're looking at n as it's approaching 1. Our A value is 5. Our R value is 0.9, which can be written as a fraction if you want as 9 over 10. Okay, a lot of times we write these as fractions to make it simpler for ourselves, to the power of n. Okay, so that works out great. We're going to plug it into this equation. This equation is the sum, so it's going to help solve the sum of all these values. All right? So we've built the question now from this series, and now we plug our information into this question. So our A value, in this case, was 5. Our R value was 0.9, or 9 over 10, which I'm going to do in blue. Right? 9 over 10 to the power of n minus 1. And all divided by R again, which is 9 over 10, subtract 1. Okay. Now, we'll equate the bottom, and then we're going to talk about 9 over 10 to the power of n specifically. Okay, so 9 over 10 subtract 1 is going to give us, do you know off the top of your head?
Negative 9 over 10.
Not
negative.
Close. It won't be 9 over 10, but think of this like
negative 1 over 10?
Yeah, that's right. Think of it like I just kind of quickly changed this to 10 over 10. We subtract, becomes negative 1 over 10. Good. I like working with fractions because at the end we're going to do some division, which we can do without a calculator. Now, this value here, 9, 10 to the nth number, is approximately what value? Well, we'll take out a calculator to try to simulate something very similar to this. Now, 9 over 10 is 0.9. Great. to the power of an infinitely large number. Okay, so say we put it to the power of infinite. It's essentially 0. And we've talked about this before because it's a value decreasing, or we're multiplying values that are constantly decreasing. So this is approximately a value of 0. So we can replace this entire number with the value of 0. So we have 5 times 0 minus 1 all over negative 1 over 10. 0 minus 1 is negative 1 times 5 becomes negative 5. You okay with that? All divided by negative 1 over 10. Well, this is where reason I kept it in a fraction. Because this is a division sign, let's just divide fractions. This becomes negative a fifth divided by negative 1 over 10. And when we divide fractions, we multiply and invert the second number. And I'm just going to turn a fifth into a fraction. So negative 1 over 5 over 1 times negative 10 over 1. The 1's multiply. They're relevant. Negative 5 times negative 10 is going to be positive 50. So the sum of this series is a value of 50. Okay? And that's how we built the equation from the actual values in the series.